Hello, today we're going to talk about energy and power. We've talked about work. Let's see how work and energy relate together. Energy is an object's ability to do work. So, if an object has energy, it can do work. Okay, think about this. If a car is moving, can it run into something and do work on another object? Of course. If an anvil is flying through the air and lands on a spike to make a railroad, is that doing work on the spike? Of course. When you swing a hammer and it has potential energy when it's up high, kinetic energy as it moves down, are you able to nail a nail into a board? Of course. So whenever an object has energy, it is able to do work. Let's talk about some different kinds of energy here. The first one is kinetic energy. We know this one from the work energy theorem. Well, it's a quick reminder here that the energy of motion, kinetic energy, is equal to 1/2 mv squared. Energy is measured in joules, just like work is. They relate together equally. If you were to plug in the units here for mass as being kilograms and the velocity as being meters per second and squaring that, you'll get that Newton meter or that joule out of it. We have a couple kinds of potential energy, which is the energy that an object has based on its position. If an object is in a gravitational field, it has potential energy. In our equation for that, I put PE with the little g down here, so we know it's gravitational potential energy. And that's equal to an object's mass times the acceleration due to gravity times the height. If you think back to when we talked about work being done by gravity, you'll notice that's the exact same equation. Work done equals the change in gravitational potential energy. And then finally, we have spring potential energy. Spring potential energy, we're going to put PE with a little s for a spring. That equals 1/2 kx squared. Now let's quickly introduce these terms real quick. K is what's referred to as the spring constant, and x is the distance that a spring is compressed or stretched. So distance of compression or stretch. Kinetic energy and spring potential energy must be positive. If you look at the terms involved, mass is never going to be negative, spring constants will never be negative, and we're squaring the other terms. Therefore, Ke and spring potential are always going to be positive. Gravitational potential energy can be negative based on where your reference point is. If your reference point for gravitational potential energy, let's do a little diagram over here. Let's say we have some kind of hill, mountain. And if your 0 point is up here, where PEG equals 0, then anything below the top of that mountain is going to have negative gravitational potential energy. So based on the reference point, you can have negative gravitational potential energy. Another kind of energy that's not mechanical energy, this is what we looked at before, our types of mechanical energy, is thermal energy. And thermal energy is the energy that is lost in a system due to friction. Friction is an example of a non-conservative force, meaning that the energy is not conserved in the system when we have friction present. It's equal to the work done by friction. So if you're thinking back to our work equation, we know that work is equal to force times distance. So if we're looking at thermal energy, I'm going to put an E with a little th. That's equal to the work done by friction, which is just going to be the force of friction, times the distance over which the friction acts. So we talked about one of our problems before about the work done by friction. We can really relate that to force of friction times the distance. Alright, conservation of energy. Energy cannot be created or destroyed, only converted to different forms. You've probably been hearing that since you were in elementary school. Why is that important though? And for our purposes, for a system, energy will be conserved unless friction is present. So we can set up a relationship that says that the amount of mechanical energy in a system initially is equal to the amount of mechanical energy that will be present after some change, plus whatever is lost due to thermal energy. Mechanical energy, there are different forms of mechanical energy. Let me go back a couple slides here since I didn't really highlight that real well. And that says mechanical energy can be our kinetic energy, it can be our gravitational potential energy, or it can be our spring potential energy. Those are our three different forms of mechanical energy we'll deal with right now. So when we say ME, we can expand that out to be KE initial plus gravitational potential energy initial plus spring potential energy initial, which will then equal KE final plus PEG final plus PES final plus that thermal energy that's lost. Okay, we put the thermal energy over here. We're going to make it positive on this side. Okay, it just allows us to make sure that all of our energy is accounted for. It is not mechanical energy. That's why it's not included in the ME, but it is present over there. You will not have every single one of these types of energy in every single problem. Okay, we'll look at an example here in just a second, and we're going to be able to use this equation to solve for a different variable. However, you will not have this every single time. Okay, that's something that you need to make sure that you're aware of. You're not going to use all of these forms of energy every single time. So here's our big expanded out form of this. If an object is moving, then we know it's going to have kinetic energy. If it has height, okay, like if the vertical position is changing, then you're going to have PEG. If there's a spring that's being compressed or stretched, then you're going to have PES. Okay, so just keep those rules in mind. Like I said, you're not going to have every single one every single time. That would get a little crazy. But make sure that you are paying attention to when you do have these forms of energy present. We're going to look at an example problem here. And we have a 20 kilogram ball that has an initial velocity of 12 meters per second is thrown down from a 15 meter tall tower. If the speed of the ball is 19.1 meters per second, when it reaches the ground, let's put it this way, okay, when it reaches the ground, it's 19.1 meters per second, how much energy is lost due to air resistance during the ball's flight? So the first thing I'm going to do is draw a diagram and try to determine what kind of energy I have here. Okay, so I have a 15 meter tall tower. My ball up here has an initial velocity of 12 meters per second. And down here it's going to have a final velocity right before it hits the ground of 19.1 meters per second. Okay, so let's think about this for a second here. It starts off with some height. So we know it's going to have some initial potential energy. Okay? It starts off moving. So it's going to have some form of kinetic energy initially. It's going to fall through the air. Then right before it hits the ground, it's still moving, so it's going to have some form of final kinetic energy. And the question asks us to determine how much energy is lost due to air resistance. Okay, that means we're going to be solving for thermal energy. Okay, whoop, I didn't want to use that one. So we're going to solve for ETH. Okay, because it is at ground level and our reference point down here is going to be 0, then we know there's going to be no final potential energy. Okay, so we're going to use our conservation of mechanical energy relationship, and we're going to say ME naught equals MEF plus ETH. Okay, mechanical energy initial. In this case, we have initial kinetic energy because it starts moving. Okay, it's not at rest. We also have some initial height, so it has initial potential energy. We know it's going to be moving right before it hits the ground. And the question asks us for thermal energy. If this was the case where our air resistance was being ignored, then we would have no thermal energy. Okay, so keep that in mind. So now we're going to plug in kinetic energy initial is going to be 1/2 mv naught squared. PE initial is mg times h initial. KEF 1/2 mvf squared. And ETH is what we're going to solve for. Now I'm just going to plug in my variables, and we're going to be able to determine what ETH is. So 1/2 20 kilograms times 12 meters per second squared plus 20 kilograms times g times 15 meters, which is our height, equals 1/2 20 kilograms times 19.1 meters per second squared plus ETH. So I'm going to go ahead and plug through, and I'm going to say 0.5 times 20 times 12 squared. That's 1,440 joules. So right here, 1,440 joules plus 20 times 9.8 times 15, which is 2,940 joules Okay, on our final side, 0.5 times 20 times 19.1 squared, which is 3,648.1 joules plus ETH. Okay, so on my initial side, I'm going to add up 1440 plus 2940, which is 4380. Then I'm going to subtract away 3648.1, and I'm going to get that my thermal energy that is lost as the ball falls is 731.9 joules. Okay, so we solved the problem. Not too bad there. Okay, those of you that love using kinematics, the reason you cannot use kinematics on this one is the fact that we do have air resistance. If there was no air resistance, you could have done kinematics. However, we're asked to solve for something that involves air resistance, therefore we can't simply use Vf squared equals V naught squared plus 2a delta x. Okay, so a pretty straightforward example problem. Make sure you're drawing diagrams, make sure you're showing all your work there. One last thing, power. Power is the rate at which work is done or that energy is used. Okay, whenever we have a rate, we know that we're dealing with something per time. So power, capital P, equals work over time. All right, or change in energy over time. Okay, work is measured in joules. I'm going to do my units over here in blue. Time is measured in seconds, and 1 joule per second is 1 watt. Okay, you've probably heard the term watt before in dealing with light bulbs. The greater the wattage on a light bulb, the greater amount of energy that's dissipated every single second. So you have a 60 watt light bulb versus a 30 watt light bulb, it's going to put off twice as much energy every single second. Okay, so power is capital P, it's measured in watts, and that's equal to a joule per second. Alright, so keep that in mind when you're working these problems out. There'll be some other things you may want to look at. You may have to expand out that work. You know, the work equals force times distance over time. Okay, so keep that in mind as well. You never know when those equations may come in handy. Okay, so there you go, power, pretty simple stuff. That's a rate. Remember, rates are with respect to time. And that's about it for that one. Hope you enjoyed this wonderful video about energy and power. Thanks!